game, so I have to do something else to try to keep you guys awake. Uh, oh, thank you. Thank you, first of all, to the organizers of this conference for inviting me, especially Selvam, Ahad, Arvind. It's great to be here. Um, when I was talking at the AIA Center for Architecture, the question was, does the architectural language actually begin to respond and begin to take its own shape when we're talking about sustainability or green architecture? Just right off the back, I'm going to say my answer is no, right? And hopefully through this presentation, as I give you the case studies, I'll be able to explain to you why I say that, and hopefully it'll be clear to you why I think that there is no specific language for sustainability or for architecture. It's reading a little bit strange on the screen here, but I'll read it for you. So I start with the basic question, right? We talk a lot about sustainable design, green design, high performance design, you call it whatever you may, but what exactly does that mean? And to each, we all take away, we have all our different answers and different perceptions of what we think it is. To me, as an architect and a designer, it is nothing more than good design practice, right? You may say I sort of believe in kind of grabbing the low-hanging fruit here, but the reality is that if we design things properly, we understand that creating a built environment which would respect and respond its external as well as its internal environment is the right way to go, right? And it's nothing new. We have been doing that for about 1,000 years or so, right? We look at any examples of historic architecture in India is there. This is a building skin in Fatehpur Sikri from the 15th century, I believe. Don't quote me on that. But so it's been around. So we know how to do this. We have been doing it for ages. So what's different today? What's specifically different today in India in the past decade or so as the market has changed, as the environment has changed, as the industry has developed, and you look at certain issues that may be different from what they were about 100 years ago or 200 years ago, right? So I've listed down a few things. The building typologies are different. We're no longer just building palaces and homes. We're designing office buildings, airports, convention centers. So the program of these spaces is very, very different. The internal use of the occupants, the way we use offices, is very different from what it was 20 years ago, right? Nobody had computers 20, 25, 30 years ago. Now we're designing spaces which need to respond to the way we work. You don't need 500 lux of lighting in a space where you're using computers. You may need much concentrated lighting on the bench. Occupant comfort needs. Unfortunately, I think we have changed, and I am as guilty as anybody else, but look at us. I'm wearing a suit in Chennai where it's probably, 98 degrees Fahrenheit outside, right? Can't convert that to Celsius in my head yet, but it's fairly warm, but we're changing our sort of habits and needs. So we go to offices, whether it's Hong Kong, whether it's Chennai or Bombay, we wear suits, and when it's 35 degrees outside, we want to maintain 16 to 20 degrees Celsius inside. So that starts to become a problem in my opinion. And there's a whole topic we can go off on tangent to talk about the thermal comforts and what the standards are and what should actually be happening. And then the use of technology. And the use of technology comes in different ways. And I think apart from the user technology in a building, I think when I say use of technology here, I think I'm talking more about technology when we are designing a building, or we are operating a building, or we are constructing a building, right? So we have some advantages today, and this is a pyramid diagram that I've seen it in various kind of situations before, but I kind of apply that directly to designing a facade, and it's fairly simple idea. The more we can do early on when we are designing a building, the more potential we have in saving the energy. The later we get, the worse, the more expensive it's going to get, and the impact on energy savings is going to be very, very minimal. So in a lot of ways, for architects and designers, it's a heavy load on us. I mean, if we get started on the right foot, if we do the right thing early on when we're designing a building, we are going to be much better off. We're going to be saving a lot of money. We're not going to be investing in super high-end technologies, and you could still achieve a high-performance building. And then there's obviously the connection between the soft technology and hard technology. And what I mean by that is, soft technology is tools available to us today as designers and architects. If we spend a little bit extra time in doing the right analysis work through various energy modeling simulation tools, we use the right parametric design tools to run 100 iterations instead of 20 and analyze them correctly, we'll be able to do a lot of these things at a much cheaper way. Whereas as you move on to hard technologies, then it's costing you more and money. But that's the gradual progression. So if you do the first step, you use the soft technology and get the design and the architecture to the point where it's already efficient, then you apply the hard technology, then you've got a much farther way to go. So what I mean by soft technologies that are available to us today include anything from as basic as Excel. We analyze a lot of climate data, a lot of numbers that come out of whether solar radiation analysis or anything like that, and we can very quickly convert that into something that means something graphically. You instead of reading 1,000 numbers, for example, in climate data, if I chart it out in, for example, on the top left side over there, you start to read patterns over a year about when does it get more humid and when does it get less humid, or when does it get the temperatures go up, how do they relate to each other. So those kind of patterns, and the idea really is to take those numbers and make them into something that we begin to understand what it means and really convert that into the design, right? So why talk about facades then? And I've focused on facades for the last, 6-7 years now. And the basic point is, as an architect or even as an engineer, when you're designing a building, the biggest impact on your peak load demands in a building will come from the facade. Now, whether it's conductive, radiation, convective, you can analyze that, and we can run these studies and look at different climates, whether it's Abu Dhabi, New York, or Mumbai, or Chennai, and you can get into the specifics of it, which allow you to then come to a design solution. And I'll give you a simple example here. I have two pie charts there. One is Abu Dhabi, one is Mumbai. And both of them, if you just think about the climate, they're pretty much the same. Abu Dhabi is also humid and hot, and so is Mumbai. And you would think that the architectural facade response should be the same. But when you look at these pie charts, you begin to see the difference, and you realize that in Mumbai, the majority of your loads, your heat loads, are coming from radiation rather than conduction, right? So what it means simply is that when you're talking about conductive transfer, we got to worry about the U value of your external wall, which means that you probably want to reduce the amount of the windows. Whereas in Mumbai, I could probably go as much as I can in terms of the window sizes to a limit, as long as I made sure that there was no direct solar radiation. So there's immediately these kind of information, this kind of data allows us to move in a design direction, right? But obviously performance is not the only one issue that we have to concern ourselves with. So when we're designing a building, we always look at performance, aesthetics, constructability, feasibility, financial feasibilities. A lot of those issues come into play, but the point here is that it's not just one. It's never just the aesthetics. It's not only about making it pretty, it's also about performance. It's not only about making it performative. It has to be feasible construction-wise, financially. All of those things come into play. And then there's one, the diagram is a little bit small there, but one thing we have started to do is what we call a multi-variable trade-off process of design, where we're beginning to combine a bunch of different tools. So we start with, for example, we design in a 3D modeling tool called Rhino, which can now gets linked up to another add-on software called Grasshopper. For some reason, they're all named after animals. Don't ask me why. But so the idea is that Grasshopper allows us to script things where we can plug in, data, radiation data coming from Ecotech, We can plug in a design aesthetic idea that we want to have, or even program that's happening. So in this case, there were 3 different elements that were brought in, and that Grasshopper tool, which is basically a scripting tool, allows us to moderate this the design outcome, giving it different variables and such. So you can get into a lot of these things, and what it basically allows us to do is, take everything into. It's not that we're letting the machine design it for us, but the machine allows us, gives us 100 different design iterations instead of 1 or 20, and that allows us to look at 100 different options before we can say, okay, we like this one, this, and we can compare each other in terms of its design aesthetics, in terms of its performance, and then come to a conclusion. So I'll start with my case studies, but before I get to my main case study, which is a Carle is an office complex in Bangalore, which we are working on right now, which is under construction. I just wanted to point out a project which is happening right here in Chennai. It's a corporate office building, very small, about 10 to 15,000 square feet, but a very interesting project nonetheless for us. Fortunately, we have Selvam and his team working on this, so I'm thankful that we are getting very close to him. I don't have the renderings for this project right now, but if you saw the rendering and the final product, they are very, very close, which is a great achievement for us. And it's not completely done yet. Now you may ask, I talk all about sustainability, and here it is, we have a glass building in Chennai. Unfortunately, this was a design that got preferred and picked by the client, and we said, okay, we'll take on this challenge and we'll try to do something that, a glass building in Chennai, and try to figure out how we can actually do it. So in this case, we kind of relied on a little bit of latest available technology. We found the highest performing glazing in this, and because, like I said, radiation is the biggest impact, we were more concerned about the SHGC value rather than the U value. So here we got something that is a SHGC value of like 0.25 or something. Then we added a custom frit pattern on the glazing. So now we're trying to combine aesthetics with the performance, right? And the way the frit pattern actually is applied to this building is in a similar fashion that I explained earlier. So it takes into account where the maximum amount of radiation is being hit, but that's not the only thing. We also take into account where do people want more views. So sometimes it's a little bit reversed, where you may find more open glazing up on top, but that's also a compromise for us because that's where the corporate office are, that's where you get the views, so obviously we have to. So it's always a balance between various parameters within a design process. Nonetheless, I mean, even after doing this thing, and there was no requirement for our team to do any kind of energy modeling or any kind of performance testing, we took it upon ourselves to do this. And we ran a quick study, even without running a full energy model. We ran sort of an analysis and a base case comparison, just as you would for any lead project. But instead of running it for energy modeling, we ran it for solar radiation. Knowing that solar radiation will, in the end, amount for the maximum heat gain in the building, the thesis was, if we could prove that we're getting less radiation into the building as compared to an ASHRAE base case building, then we are, theoretically performing better than ASHRAE base case building. And we did manage to prove that. I don't have the exact percentage, but we were performing better than ASHRAE base case building, and primarily because we applied this glass only on 2 sides of the building. We avoided the other 2 sides, and hence we got overall percentage of glazing was still not as much, plus the fact that we used high performance glazing, we used frit patterning, as well as channel glass that will eventually show up on this building. It's not there yet, but there's also another layer of channel glass that will come in front of the primary facade. And the whole idea of that channel glass is that it allows some deflection of light and some deflection of heat. Some of it very hard to prove theoretically in modeling right now, but perhaps maybe when it's done, we could come back and do some actual empirical testing on the site and understand how it functions in this climate. So here, that was an example of trying to bring everything together. It's not just about design, it's not just about performance, it's really about both. And they have to, it has to find the right balance to do that. So with that, I'm going to move on to my main case study here. This is a project for SEZ office complex in Bangalore. The site itself was master planned a few years ago, and fortunately for us, it was planned well. The site that was given to us and the massing was kind of given to us had the right orientation. We had mostly north and south facades and very little surface area of the facade on the east and west side. And we started working with the client, and the client said, great, you come and work and give us a design on these two particular buildings, but nonetheless we want to see what there should be a story about the whole SEZ site. So we took the same environmental story and in a more spiritual way kind of defined these 5 buildings that would go on the site based on the 5 elements of nature, or the Panch Tattva in Hindi. And so the first building was going to be about fire, the next is water, and so on and so forth. And the voids, or the spaces in between them, became the space. We gave them some initial ideas. The first 2 buildings are the ones that we are working on right now. Unfortunately, the massing of those 2 buildings were frozen, so we couldn't, it was based on the original master plan, so we couldn't tweak that. But then we had the flexibility to start working with the facade. So this is another modular design idea that we have been working on for quite a bit. And basically the point here is that instead of designing the whole facade at once, what if we figured out a module, and then we designed that module, and we provided enough parameters within that module that I could change as I move around the facade, right? And you could then, that particular module could begin to respond to different kinds of environmental parameters. It could respond to your solar radiation, daylighting, program, what's happening behind. Maybe you want more windows, maybe you don't, maybe you want more shading. So if we start designing on a modular basis and wrapped it around, it provided us something much richer to work with. It gave a much bigger or nicer texture on the facade. And you got the performance aspect out of it. So in this case, obviously, again, I'm going back to solar radiation because to me, in this climate, that is the key impact on the heat gains. So if we run, basically, if it's a very simple idea, is you take those 4 module types. There could be 4, there could be 10, there could be 100, depending on the budget that allows us to do. And then you scatter them around the building depending on how much solar radiation you're receiving on that particular point. Now, still doesn't mean that every building could be very, very different depending on the design of that module. And I'll give you examples. Here's some initial concepts we gave our client. And even though all of them were very different in design, they were all had the same idea of modularization. So everything could be broken down into 100 modules, and each of them could change depending on where they are on the facade. And in the one that finally got selected was a sort of a wavy pattern on the facade. And the reason we also kind of like this is it allows us to provide shading there, and it's a very simple idea. It's a simple geometry of curves that overhang on top of each other. And it gave us enough parameters that if we could work with the depth of the panels, we could work with the radii of the curve, we could work with the window wall ratios, the glazing properties, opaque wall properties. So there's enough parameters that we could tweak as we moved around the building. In this particular case, because of cost constraints, as most of you probably know, when we're talking about spec office building development, it's tough. It's tight in terms of budget. You can't really push that far. So the only thing we kind of settled down on this one was changing the window wall ratios. So as you go around the building, depending on how much solar radiation is hitting the facade, whether it's because it's on east or west facade, or whether it's because of the shading from adjacent building, the sizes of the windows would change. But also the size of the windows would be constrained to a limited size. Also, we are also studying, responding to the amount of daylighting that's coming in. So that's the other side of the balancing on that. So we ran studies on that, initial studies to look at how much solar radiation was hitting the walls. Based on that, obviously, it's intuitive, but east and west would get much smaller windows, and the north and south side would get more. Like I said, we were lucky. Our orientation was right in this project. And then we got a little bit more specific on each of the facades. These are the north and south facades, and analyzed how much radiation is hitting the walls. And as you can see, like the south facade. I'm confused now. I think it's the north facade. It's getting the shading from the adjacent building. You see the gradation quite a bit. You see that the lower floors are, much less amount of solar radiation that's hitting the walls versus the top side, and that allowed us to begin to change the size of the windows. So now what it's done is not only that we are responding to a very specific environmental condition. As you look up this facade, the windows actually grade up, and as you grade up, they get smaller and smaller. So it also begins to impact a very interesting design pattern, but it's coming out of real performance based analysis. And initially we were trying out different methods of how to construct this. We're looking at a cheapest way of doing a block wall and then just cladding this thing on. But after having consulted with a few folks, we have now settled on a unitized system. But I still bring up this graphic here because it sort of got my mind going, and this is really for you, the facade manufacturers out there, because facade. When I look at this diagram and I see, this module is becoming a sort of an animal on its own, and this is a facade module, right? Why does the facade just have to be a facade? Whatever we have done so far is only passive in its performance aspect, right? But what if we began to apply mechanical equipments in there? There are cases. I mean, we look at, there's a project in Bonn in Germany. I believe it's the Deutsche Post Tower. If you look at that project, what they've been able to do is, using a double skin wall on the outside, they bring fresh air intake directly from the skin. They have induction type units on the perimeter of the wall. They condition the space right from there. If you get the right floor plate in a building, and you condition everything from the envelope, you have no more ductwork in the building. Imagine the amount of square footage the developers are gaining for selling this property, right? So that's my question, and then that's something that I truly want to explore further, and I throw it out there to you guys is, where can this go? Why can't the facade module become a machine in itself? You no longer have any chillers in the building. Everything comes unitized in a panel. You pop it in, and the building works, right? So there's a collaboration idea between architects, engineers, and fabricators, but I think it has to come as a team solution to really take this to the next level. And the other advantage of thinking this way, I think, is we're not trying to do, there's a lot of research going on out there for technologies that are 10-year ahead, 15-year ahead. Look at solar panels. They're still not as efficient as you would want them to be. But these are technologies that are available to us today. We just have to find a way to make that work in a financial model, right? Make it work for the developer. If the developer sees I have to put no ductwork and I can gain all that square footage, maybe he'll buy into this kind of stuff. So we need to come together and kind of push this idea further. That's my opinion, anyway. So in this case, we ran our, again, solar studies on each of these windows. The way the windows are placed is you always get sort of a bit of an overhang above and a side shading system. They're always kind of, the panels, the vertical panels that come out are usually on the west side, which allows us to get more shading on the glazing. So we did that analysis, and we found that in the summer months, which are the ones that we are more concerned with, we're getting about 81% shading during those summer months, which is quite good, right? And I'll show you how that impacts the energy load. So we ran a full energy analysis on this building, and just the shading, impact of the shading is 3.1%. Now that may seem small, but imagine this is an impact coming from absolutely no capital cost investment. It is all part of the design process, right? Now, if we take that further, right, if you start to include the properties of glazing, the shading, the insulation, all of those factors, of the 28% projected savings on this building, we have about 17% reduction just by the facade, right? So that's the amount of impact we can do just by designing the facade right. I haven't included any mechanical systems. I have not, upped the cost, anything. We are still competitive, by the way, on this, facade design to most of the other developers in the area. So that's the idea, and we can't underestimate the team effort here. Apart from what we are doing in the facade, we had engineers who work with us, and we found a way, even inside the building. This diagram here on the right explains that there's actually no air intake ductwork into the building. We put in lieu of a ductwork system and a fan, we put in a huge, not a huge, but a sizable light and air shaft. And what that does is brings light into at least the top 4 or 5 floors of the building, additional daylighting, and also brings in fresh air that go directly into AHU rooms adjacent to these air and light shafts. So you eliminate all the fans requirement. Also, the shaft is helping pressurize the stairs, helping pressurize the elevator lobbies. So again, we're reducing a huge amount of duct work. We're reducing a huge amount of fan power required in the building. The next few slides are just some renderings and images of what we have done. And it's so apart from talking about just performance, the idea here was that we designed something that actually begins to self-shade and perform by itself. So I'm not designing a glass building and then trying to add shading devices and try to prevent it. I've tried to take the first step nicely or correctly. The other thing that really pleased me about this design was, even though it's a static facade, it has a very dynamic quality, because we're relying on the position of the sun to change the shadow lines on this building. So imagine, the way these things are, depending on the time of the year or the day of the time of the day, the shadows will always be different. So whenever you show up in this building, you may always find something that's or a perspective or a view that you may not have seen before, right? So it's got a very dynamic quality to it. There's a few more renderings. We had the idea about that fire and water, and as you can see, even though the buildings are identical, there's a bit of that color hue that we want to bring out in the lobbies that begin to define those two ideas. Here's a view sort of in between these two buildings. Each is about ground plus 11, so about 12 floors, double height lobbies, and a plaza in the middle. So the building is now under construction. I believe last time I was there it was 4 stories, but on the phone call I just found out they're up to 7 floors now in terms of the structure of the building. The curves, the slab itself is curved, and again, it's a simple geometry. You begin to repeat it, it becomes fairly easy to do, and then the rest of the facade will become a unitized system, including the roof of the niche that sticks out. There's another shot of that construction site. So my biggest concern was making sure that we get decent, curve lines on the slab edge condition. And considering other projects I've seen in India, I think this came out fairly clean. So hopefully the facade fabricator will have less of an issue adjusting things here. This is about floors up, and as you can see, the curved areas, the rhythm is coming out nice, and hopefully the final product will be as decent as it looks in our renderings. Fairly large site, but the first building is up with a 3 basement podium. That's it. Thank you.
Questions? Yes, do we have any questions from Mr. Kohli here?
Am I allowed to ask something? See, this was definitely a wonderful design. I mean, as a layman, I could, as much as I could understand. But I wanted to ask, being a dweller of any typical building, glass building, normally a facade building, like how important these days, everywhere we see all the typical glass facades, as you said, we're building, glass jungles everywhere and stuff like that. So how, I mean, is it really relevant to have 60% or 70% window to wall ratios?